So the subsystem hazard analysis technique, it comes on the heels of the preliminary hazard analysis. Hazards identified and analyzed in the preliminary hazard analysis will be transferred to the subsystem hazard analysis technique, and it'll be analyzed in greater depth there at the subsystem level, because during detailed design phase of the system life cycle, more information is known about the system than in the preliminary phase. Hazard analysis then can go to a deeper level. So along our flow diagram, you'll see that at the time the subsystem hazard analysis is conducted, we're starting to get some practical benefits out of the efforts, these hazard analysis efforts, in the form of some corrective actions. So some of the outputs of subsystem hazard analysis will generate corrective action that then can flow back into the design of the system. The system design can give us some preventive measures, design adjustments, and safety recommendations that will help early in the design process to eliminate or mitigate some of the identified hazards. Inputs to the subsystem hazard analysis technique are conducted during the detailed design hazard analysis type. So they're conducted during the detailed design hazard analysis type, and the inputs then come straight from that preliminary design hazard analysis type. Outputs from the detailed design hazard analysis type are in the form of subsystem hazards, mishaps, causal factors, risk, safety recommendations, and top-level mishaps. Notice, too, that an output line of the detailed hazard analysis type goes to the requirements design. We're going to talk about that in the third video that goes along with this presentation in just a little bit. A new worksheet is started at each subsystem level, which is the hazard source item level. Keep this in mind. Functional hazards will only be analyzed during the subsystem hazard analysis if those hazards do not cross over into other subsystems. So we're looking specifically at the subsystem, perhaps even the component level, and functional hazards, things that the system is supposed to do, will only be analyzed during this technique if those hazards do not cross over between subsystems, because we're going to be looking specifically at that subsystem level. We're not looking at the forest here, we're just looking at the trees, but we will look at the forest in a little while. So the subsystem hazard analysis, it looks at hazards at the subsystem and the component level. It's very detailed. And here's what that's going to look like. Remember the ACE missile example from our text in earlier presentations? Here's the indentured equipment list from that ACE missile example. So the missile is the system level. Structure and warhead, all the bullet points, those are the subsystems. As such, a new SSHA worksheet will be initiated for each bullet point. For each of these bullet points, a new worksheet will be initiated. Further broken down, though, the subsystems are broken into units. Units, assemblies, and components. Remember that hierarchy discussion that we had from week 1? This is an example of that. So the missile is our system. Structure, in this case, is our subsystem, and then that is broken down into the structural frame, skin, deployable fins, and flight controls, which in this case are units and assemblies. So that is the further detailed depth that we get into with this subsystem hazard analysis. I took the example from subsystem 1.0, the missile structure subsystem, to show how those lower level items are integrated into the subsystem hazard analysis in your text. On the left side of the slide is the missile structure subsystem and the related components. On the right side of the slide is an excerpt from the ACE missile SSHA example in your text. Notice how pertinent lower level items are represented on this worksheet. Frame accounts for some of the causes. You see that here, here, here. Flight controls as well, so that we have flight controls as units. Flight controls account for some of the causes. Also note, please, that the hazard column has been taken straight from the PHA. This here, that hazard column, you can look back to the PHA example in your text and see that these hazards comes straight from the PHA. That's what we mean by it flows. The outputs of the PHA go directly into the SSHA. There's nothing that prohibits you from rephrasing the hazard if you have new information by the time you conduct this analysis, but essentially hazards are copied and pasted over from the PHA. You can rephrase them. This is actually the HS, the hazard source function or component of the hazard. So if you have new information and you want to rephrase that by the SSHA, you can, but essentially hazards are copied and pasted over from the PHA. After that, other hazards are identified through the analysis of subsystems, units, components, and those are identified typically with the use of some hazard checklists. In the causes column of the SSHA, one of the goals of this subsystem hazard analysis is to provide more detailed hazard causes. Hazard causes, remember, is the IM component of the hazard, the initiating mechanism. By this time you know more about the system, so causes should be more detailed than in the preliminary hazard analysis. And here's a comparison of from the ACE missile example in your text between the PHA example, that was the top, and then the SSHA down at the bottom. You see how the hazard causes have gotten much more detailed and more specific in the lower level subsystem hazard analysis. The other goal of the SSHA that I wanted to point out is that risk estimates are refined and recommended actions are more enhanced. With more system knowledge, refined hazard causes, that's the initiating mechanism, refined hazard causes can help us generate more refined and improved recommended actions, and that's actually the key. The recommended action is what we're striving for. The recommended actions are then going to be used to make our system safer. So the detail in the recommended action is crucial to the success of these safety efforts.